it is. And we'll put the link on the EGO website with the presentations, so you can go back to it if you want. And it's every 2 months that we are aiming at doing these webinars. UG2 is also, so it's 1 month, 1 month. And we are open for new topics. So if you have an interesting subject to present, just tell me, and we'll make sure that you can present, because it's a great place to show your work. It's not very formal. It's just building the community and sharing together with all the experts all around the table. So today we have 3 presentations. So the first one is from Martin from Voto. It's about glider observations of dissolved methane after Nord Stream leaks in the Baltic Sea. That will be the first presentation. The second one from Barak Erut from the Israel Oceanographic and Limnological Research Institute on tar pollution events in 2021 at the southeastern Levantine oligotrophic basin, with the short-term impacts and operational oceanography perspectives. And the final one by Ezi Gildor from the Hebrew University of Jerusalem on operational assimilation of glider temperature and salinity in a mesoscale flow field, Eastern Mediterranean test case, illustration of the effect on pollution dispersion. So this should give us a nice overview of what can be done with the gliders to have some pollution monitoring of different types of pollution and different ways to do it. So that's all for me. I will be very quick, and I will very quickly introduce Martin, that very kindly sent a small presentation. So Martin is working as a data scientist for Voto in Gothenburg in Sweden. His background is in oceanography and atmospheric science, with an insatiable hunger for new and exciting data processing pipelines and visualizations. So we should have nice schematas. Even though some evil oceanographers call the Baltic a dirty, shallow pond, for him, it's his home, and he cares a lot about it. And after a detour into polar oceanography during his PhD, his focus on the sea is close to his office, and gliders are a perfect tool for this, to catch both short-term variability and long-term monitoring needs. So, Martin, the floor is yours. You have 10 minutes, and then will be 10 minutes questions.
Great. Thank you so much for this introduction. I hope you can hear and see well.
It's perfect.
So this is some work that we did as a follow-up. It's the Nord Stream. So it started in 2022 when the Nord Stream sabotage happened. We started to monitor. As you can see here on the title screen, the co-authors, and this is a publication that is currently in review for Nature Communications. So I'm sure many of you remember the Nord Stream sabotage, at least from the media and the surface of the Baltic Sea. It looked something like this: a lot of natural gas bubbling through the surface of the Baltic Sea with a diameter of several hundred meters, and of course this added some pollution to the Baltic Sea. Shortly after this leak started, we went there and collected in situ measurements with our gliders continuously after the events for about 3 months. Today I will present you these observations and then some modeling that I did based on these observations. So the Nord Stream consisted of 2 double-strand pipelines, so 4 pipelines in total, and they were built to transport natural gas from Russia to Germany. They were sabotaged the 26th of September in the Bornholm Basin at about 70 meters depth. So because this is relatively shallow, a lot of the methane, the majority, escaped to the atmosphere directly, but also some of it dissolved in the seawater and then spread with the currents of the Baltic Sea. And this is what this presentation is about. Possible impacts of this are an ecosystem response, some turbulent mixing and upwelling from all the bubbling methane and the local deoxygenation of the water. We collected our observations with Sea Explorer ocean gliders. We deployed them just outside of the 5 nautical sea miles exclusion zone downstream of the leaks. In this relatively shallow waters, we get 1 vertical profile about every 15 minutes with the variables that we collected, temperature, salinity, pressure, chlorophyll, oxygen, and last but not least, the methane concentration that we collected with a Franetic methane sensor. Now, operating the gliders in the Baltic Sea is a bit special because it is relatively shallow and we have the very strong horizontal density gradients. The Baltic Sea water is brackish with about 7 PSU at the surface and up to 16 in the depths. And it also has a relatively high levels of hydrogen sulfide in the deoxygenated depths, which is not only toxic to the marine life, but also quite bad for the sensors of our glider. Now, this is a short impression how it looked like when we deployed our glider in the Bornholm basin from our small boat, relatively close to the leak site. And I'll start with showing you an overview map about the Southern Baltic Sea. You can see in gray how the pipeline is running on the bottom of the Baltic Sea with the leak sites, the orange crosses, and our glider transect is a white bar. And then there's also the red line. That's another measurement that was going on at the same time from a ship of opportunity that collected surface measurements. Zooming into the map and showing you the first week of glider data. We had our first glider in the water at the 5th of October, so a bit more than a week after the leak started and just a couple of days after the surface bubbling keys. And then I show in the colors on the upper panel the methane concentrations on the logarithmic scale, and in the lower panel the same just over time. So you can see shortly after deployment we have methane concentration of well above 1 micromole of methane per liter, which is 100 to 1,000 times more than you would naturally expect in the Bornholm basin. So we can be sure it is from the Nord Stream. Then, while our glider was moving away from the leak site to the southwestern turning point of our trajectory, the concentration dropped a lot. You see this sharp gradient in the time series. That's because the advective signal of the dissolved methane hadn't really reached that point by then. During the following 2 weeks, the concentration stayed quite high, often over 1 micromole per liter. And eventually they started to drop until in the start of November, they were about at 20 to 50 times the natural values. And another 15 days later, they were quite much back to what we consider natural concentrations in the Bornholm basin. But we continued our measurement for a while. We see sometimes it's patches of enhanced methane concentrations. And eventually in December, the exclusion zone around the leaks was lifted. So we were able to steer our glider directly over the leak sites. And interestingly, we still had observed very high concentrations, 1,000 times the natural values, right over the leak sites, which was a bit surprising. And then in the start of January, we stopped our glider observations. Now, as I mentioned, for comparison, we also work together with a group that has this data from the ship of opportunity along the red transect, and you can see how this data looks in a Hofmöller diagram, the surface methane concentrations in panel B. And then panel C, I compare the glider observations, the blue line, with the observations from the ship of opportunity, the colored dots, and they agree quite well. We don't expect them to agree perfectly because glider and ferry are luckily never at the same place. That would be very dangerous for our glider. But since we are a bit closer, we expect that we measure somewhat higher concentrations, and that's what we see here. Then having a look at the depth distribution of the methane, you see that it is in panel C and panel D kind of exponentially decreasing over time due to that it's spreading out, advecting, diffusing, and outgassing through the surface. It is relatively homogeneous in the mixed layer and has a maximum just below the mixed layer, and in the depths, like below 50 to 60 meters, it's less dissolved methane. But really the main dependency is on the time and space. So based on this data, I run a simple numerical model, a Lagrangian Shannon-Fate and transport model, which is driven by a pre-existing ocean model from SMHI, a Nemo Nordic 2 model, winds from ERA 5 for the outgassing, and then the main processes that are happening are advection, diffusion, and outgassing, and then there's also a bit of optional bacterial uptake, oxidization going on. And already with this very simple model, we were able to meet our measurements quite well. We can have now from the model, of course, a big advantage that we have the data everywhere, so we can fill in the gap and see how it's spreading now in the Bornholm basin. And you see at the bottom that the model and our glider observations fit quite well together when it comes to the column averaged methane concentrations. We get this relatively high level that eventually after a while start to drop exponentially. And after about 1.5 months after the dissolved methane starts to spread into the neighboring basin, for example, to the left into the Arkona basin and to the right into the western and eastern Gotland basins. So what we can learn from this study is, of course, the exposure of the different regions to the methane, for example, the different basins. But also some marine protected areas that are located in the regions. We learned the methane pathways. Most of the methane has apparently outgassed because the mixed layer is deepening during autumn and taking up most of the water volume. And of course, there's some uncertainties when it comes to how much of the methane is remaining for a long time, how much is outgassed, and interestingly, even after a couple of weeks after the event happened, the outgassing rate through the surface is still as high as 50 tons per hour, depending on the wind speed and first hand, of course. And finally, we can estimate how much methane there was initially dissolved in the Baltic Sea, which we estimate to about 10,000 tons of methane, with initial concentrations of up to 100 millimole per liter. So with that, I want to thank you. And I will also want to remind you to register or send your abstract for the International Underwater Glider Conference that is hosted by VOTO this summer.
Thank you very much, Martin. It was very, very insightful. And yeah, go to the Underwater Glider Conference. That's the place where we will all meet, and it's better than by Zoom. We have some few minutes for questions, like 3 or 4 or 5 questions. Who has questions? Just raise your hand. I don't see if there are any. But I see Laurent Mortier.
Yes, thank you, Martin. So quick question. So I didn't get if you have gone directly through the plume during the different transects.
The plume is ejected from the leak sites and shows our glider trajectory so that we estimated that the main current direction would transport the dissolved methane to our glider. But of course, we could have missed some that is ejected outside of our glider trajectory. And one of the uncertainties in our study.
Okay.
Go directly over the leak from the start because there was a 5 nautical sea miles exclusion zone.
Okay, there was an exclusion zone. Okay, I missed that because my question was about the vertical structure of the plume. So there are models for these kind of leaks, gas leaks that dissolve, but I haven't done the full literature, but Victor did some project on that with Total, and it's not an easy problem. So my question was really if the glider could have a better insight of the vertical structure of the plume, but for sure for that you have to go really through the plume itself, and that was not feasible.
So what we have only the vertical profiles that are most of them at least about 5 nautical sea miles away, and then only a couple of months after the event we get a profile from directly over, but then it's not really original distribution anymore, of course. Okay.
And you chose to only monitor one location, or the other one you just couldn't, or you just had one glider maybe?
So the glider is going back and forth along this transect, which is I don't quite remember, maybe 30-40 kilometers long or so. It would have required more effort to go all the way around the exclusion zone, of course, and then there are some problems with the depth. It's getting quite shallow to one side, and with the ferry traffic and so on. So it was feasible this way, I would say.
Okay. Barak, you have a question?
Yeah, thank you for the presentation. I assume that the sensor is measuring only the dissolved methane. Do you have any estimate about how much bubbles went and escaped, I don't know, to the atmosphere?
There's other groups working with that, and several hundred thousands of tons of methane that went to the atmosphere. There have been, atmospheric measurements. So the studies, I think I have it on an extra slide. Do I have the paper here? No, but there are more studies about like the atmospheric parts of it, and like to differentiate between like the bubbles in the water and the dissolved methane. It's not easy.
So in terms of quantities, how much escaped as bubbles and how much you measured? I don't remember the number. How many tons are dissolved and how many tons escaped as bubbles approximately?
So 2 to 3% of all methane that escaped got into dissolution according to our estimate.
Thank you.
Okay. Nice. Any other questions? Don't be shy. There's a lot of questions that can be asked. Victor.
Hi, sorry, I was muted. Hi, Martin. Just from an operational point of view, as you experience this crazy situation, what would have been the best set of instruments for you in the region if you really wanted to monitor this leak perfectly, I would say? What would you need 2, 3, 4 gliders, floats, etc.? What would be the perfect set of instruments to have the best view of this?
It would have been great to have more gliders, of course, because then we would get rid of the uncertainty that some of the dissolved methane could have ejected past our observation trajectory or to another direction. It is very valuable, I think, to record the depth information. So it's great to have like either the gliders And I think the gliders are pretty good because we can steer them opposed to like moorings or floats. Then there's also large uncertainties when it comes to like how much of the methane went directly through the water column and into the air. So I don't know if there could have been some like swimming or similar instruments that can kind of directly measure how much methane is coming out of the surface. I'm not sure if something like that exists. There has been satellite measurements and so on, but there's quite high uncertainties of these numbers actually of the atmospheric methane.
We could imagine that a wave glider or surface vehicle like this could measure what you're interested in. But just okay, thanks a lot.
Is there another question? Laurent. And
Yes,
maybe it will be the last one and we'll move on to
The very last one. So you mentioned the exclusion zone, and I know that, well, I don't know, the leak was in Swedish water or German one or maybe Danish. I don't know exactly how the EZ are, and it's a complex EZ certainly.
So there were the northern leak site that was in Swedish waters, and I believe the southern leak site was in Danish waters.
Okay, and the exclusion zone was because there was the international inquiry, I don't know, or because of other security or maybe traffic reason?
I believe that is I can imagine two reasons. One is probably the investigations that went into the area, like who has done it, the police investigations, or military investigation, whatever it is. And then of course for the ships also, because the buoyancy of the water was so reduced when it was still bubbling, and then they just left the exclusion zone in place with that, I believe.
So the clearance to get there, even outside the exclusion zone, was easy to get. So because you were there some days after the explosion, or okay, perfect.
Traffic up to 5 nautical sea miles close to the sites was permitted quite soon.
Okay, thank you.
Thank you. Thank you very much, Martin. It was very, very insightful, and I understand now that you made the measurements in the Swedish waters, which is easier for Voto, I suppose.
Yeah. Thank you.
Thank you. Let's move to the second presentation. That will be TAR Oil Pollution Event 2021 at the Southeastern Levantine Oligotrophic Basin, Short-Term Impact and Operational Oceanography Perspectives. And it will be done by Barak Ehud, which received his PhD in 1992 at the Hebrew University of Jerusalem in Israel. He was appointed Director General and Chief Scientist of Israel Oceanographic and Limnological Research Institute since 2005 to 2022. Since 2008, he's affiliated as full professor at the University of Haifa. He has published more than 180 referenced journal articles and book chapters, and has supervised 30 graduate students. And his main interests concern studies on chemistry of atmospheric aerosols, marine pollution, and geochemical oceanography. This is very impressive, and I hope that the presentation will be as well, and I'm quite sure, so the floor is yours. And you're muted.
So, okay.
Perfect.
Thank you for the introduction and for the invitation. I don't know if you see the... Okay. You see the presentation?
It's not full screen, but and now it is. It just it takes few seconds to load. It's perfect.
One moment. So now, but not in my computer. Now it's okay?
Yes, it's okay.
Okay, thank you. So thank you for the invitation, and good afternoon. I will talk in short about some operational oceanography aspects that are related to unusual and intense star pollution event that we had in 2021, in February 2021. Other aspects of this event, like, for example, the chemistry of the tar, etc., are in this publication that is shown below. So in 17th of February 2021, we observed large amounts of tar that landed beached along the Mediterranean, the beaches of Israel. It is marked in this red line in the right of the figure. This area is the eastern part of the Levantine Basin, which is the eastern part of the Mediterranean Basin. And it's unique. It's in its extremely low primary production. You can see in the left figure that it's even lower than other oligotrophic areas. So it's an ultra-oligotrophic marine system. And it also has extremely high sea surface salinity and temperature. And therefore, it's a very ecologically sensitive system for marine pollution. In addition, this area serves as the main source of drinking water for Israel. About 70% of the drinking water of Israel is coming from desalination plants along the shorelines. There are 5 operating today, very large ones, and there are 2 that are expected to operate in a few years, producing water also to the neighboring countries, for example, to Jordan. In addition, it has some sensitive habitats, like, for example, the one that is shown in the figure. It was discovered in 2021, 60 kilometers offshore at the deep sea at 1.1 kilometer water depths. And this is the first marine protected area that was defined in the Israeli EEZ beyond the territorial waters. And this area is exposed to high risks of oil spills because it contains very dense maritime traffic. You can see it in the right figure. Also, about 18% of the crude oil shipments take place through the Mediterranean. And so it has a relatively larger probability for oil spills. In addition, in the last decade, there was explorations and actually productions, exposure of new deep sea gas fields. They are marked in the middle figure with red triangles. This is at the Israeli exclusive economic zone, but also there are findings in other neighboring countries like Cyprus, Egypt, and they are planning to do a deep sea drilling in the South Lebanon. Now also to another gas field. And this gas field, it's already producing a lot of gas. There are plans to transfer, to export some of the gas to Europe through a marine pipeline. And they are accompanied with oil derivatives, what we call condensate. And therefore, they enhance the risks of oil spills in this area. At the day of the landing of the tar from unknown source, without any notice, there was a sea storm. And first we wanted to know whether the sea storm is an unusual one that maybe harm one of the oil infrastructures. You can see it on the 17th of February in the upper figure. It was about 5 meter waves, height waves, significant height wave. However, it is not an unusual as compared to other storms that we have in the last decade. So this was not the case. At the date of the tar landing along the shore, the Ministry of Environmental Protection approached EMSA, the European Maritime Safety Agency, to see whether they can check retrospectively if they can see some oil slicks from remote sensing. We also did it in parallel, also with the help of the German Space Agency. And there were some suspected slicks that are mapped in the central figure. You can see it by the different colors and numbers. The main one is 11A in orange. You can see it here, and also in the upper figure. Immediately getting this location, we run the MEDSLIC, which is coupled with the other hydrodynamic models, a forward simulation, the propagation of the slick from this 11A location. Actually, it coincides in terms of location of the TAR landing and the timing to the occurrence of the TAR. We also did some backward trajectory to get the first estimate of the source of this oil pollution. Here you can see some propagation runs of the MEDSLIC runs and the propagation of from different oil slicks that were detected. In black, this is surface oil, I would say, bubbles, and in red, subsurface oil bubbles. There were two main slicks that actually were related to this TAR pollution event. In this figure, you can see a backward simulation from this 11A and 12 slicks. This is given in black. And you can see, in order to try to estimate the source of the oil pollution, and it was assessed that it is from this region in the west. In the red dots, the green and the orange dots are forward simulations, assuming this is the main source of the oil spill, and you can see that they coincide the backward simulation. At that time, we had one glider at sea, but at the northern part of the coast, the Sea Explorer 26, without any hydrocarbon sensors. And we just got back the Sea Explorer 13, which had hydrocarbon sensor and came from repair. As soon as possible, we deployed the glider. It was on the 23rd of February. And we plan that the glider will do some transect, east-west transect from the shelf across the continental slope and try to see whether we see any signals of hydrocarbons. Here you can see some of the results that we got. There was actually, we detected an anomaly, for example, in the naphthalene-like PAH sensor. And you can see it in the lower figure, in the lower left figure. There were anomalous values higher than background on the 23rd of February. And it was decreasing gradually during 4 days till getting back to background values on the 26th of February. Most of the anomaly concentrated in the upper 200 meters. The same we got with regard to the back sweater, which may represent some organic particulates. We see an anomaly in the upper 200 meters, and then a little bit below that, and a sharp return to background values. While I'm not showing it, there was no such a signal in the CDOM. And we hypothesized that part of this profile behavior and the concentration in the, let's say, in the up to the 200 meters is related to the density profile. You can see it in the upper figure here from 2 Argos that were located at the area next to the area at the 19th of February. So it may be attributed to that. Toward the end of the month, there was another suspected leak on the 27th of February in this area, and running the model, the propagation was towards the Israeli Sea, so we decided to use the glider to target it into this area to see whether we can see some anomaly in the hydrocarbon sensor, but this leak was actually dispersed before getting into the Israeli EEC. The amount of tar in this event was estimated to be about 550 tons of tar. This is based on the cleaning activities and measuring the amount of tar. You can see it by this cumulative figure in the upper left. And considering the lengths of shorelines that we have, this is about 3 kilograms of tar per 1 meter of front beach. And we compare this amount to the amount that we had 50 years ago during the 70s, where all the area was much more polluted by oil, and that time there was no enforcement of the international conventions of oil pollution. And you can see that this event represents similar values of what was the status in the 70s. So what are the lessons from our side? In brief, first of all, we were lucky that it was a medium-sized oil spill. The large-sized oil spill is above. You can see it in the figure. Upper right figure is considered if the spill is above 700 tons. However, it's a large. It raised a flag of large alarm because there was no early warning system. It could have damaged the production of the desalination plants. They are very sensitive to oil spills. In this case, we were lucky that they kept working. So it was suggested to develop better early warning systems and operative monitoring systems, especially in areas of high risk and ecological sensitivity and valuable resource for drinking water, for example, like the Israeli EEZ. We also suggested, based on this event, that we knew that, of course, before the event, that we should develop better the simulation of real-time data into the modeling, enlarge the domain of the modeling, and maybe develop a better modeling to the area that will also consider the other gas fields and a larger part of the basin. And it was suggested that because a lot of the oil slicks that are detected by remote sensing, or even by flights, may be false detection, and they are considering only the surface water, it was suggested to the government to budget a more operational monitoring with glider that is mounted with the PAHs like sensors and the turbidity sensors and other to be able to alarm for underwater anomalies or oil signals. Thank you.
Thank you. Very interesting. There's some clappings. It was a bit longer than 10 minutes, but we'll just do a bit shorter than 10-minute questions and discussion. Who wants to ask for the first one? Because I have one very quickly. Did you manage to find where the oil spill comes from? Because you have an area? You found an
Yeah,
area?
actually there was you see this figure? I don't know. I'm
Yeah.
not in a presentation mode. Actually, there was a course data of the backwards running simulations and all the vessels that were crossing at this time. Oops, what happened? Okay, do you see now?
We can see slide 10 with the backward.
Yes, like that. Yeah. So we estimated that the oil spill came started on the 1st of February, almost 3 weeks before the TAR landing in these areas over here. And even there was a cross information of with all the vessels that were passing at that time through this area. And this is how, and also, of course, we analyzed the oil chemistry, which can give some information about the source of this oil.
Okay. Laurent?
Yes, you show some diagrams from the data from the pH sensor, which is the one the Miniflu, I guess, from the Marseille's group. Yes. So and there is a signal related, the tryptophan signal, which seems quite quite correlated to the naphthalene one. Naphthalene should represent the hydrocarbon, but why is there a signal in tryptophan which is done for something different? So is there a rationale for this coupling, I would say?
Yeah, I think that the tryptophan, all tryptophan has a fluorescence that may, of course, represent some other dissolved organic carbon particulates. So it may be related to the dissolved organic carbon that is coming from the oil, the carbon itself, not the PAHs. But I'm not sure about that. Okay. But it may be, because it's the other one. We have another sensor, forgot the name of penantren, but it doesn't work well. Okay. So we don't have the data of the penantren. We are left with the naphthalene, and the tryptophan. I am relating it to some dissolved organic carbon from the oil itself, not the PAH.
Okay, because they were on the same sensor. That's right, because it could be also a kind of, I don't know, saturation of the sensor. So it's because it's an optical sensor. So you believe it's really an organic or linked to the bacterial activity?
This is a question. This is questionable. Mm-hmm. And again, we are not trying to get an absolute numbers. We had no chance to do a validation in terms of chemistry and things like that. We based our data on other papers. There is one paper that did the Miniflow, some correlations with wet measurements. Anyhow, I think that if we are looking at the relative values, and in terms of the relative values, we see some kind of a change. Yeah.
Okay. Thank you, Barak.
Okay.
Thank you. Is there another question? One last question. It's and we can move to the last presentation, maybe. Is there anyone? Everyone understood everything? Well, I think it's good. Thank you, Barak. And
Okay.
I like how it shows that you have to be very rapid to answer to these to this pollution event because it's very timely. You have to be very reactive. And what I'm going to do is now we can move to the last presentation from ESI. It's going to be operational assimilation of glider temperature and salinity in a mesoscale flow field, Eastern Mediterranean test case, illustration of the effects on pollution dispersion. And ESI is a professor at the Hebrew University of Jerusalem. His research interests focus on interdisciplinary problems in oceanography and climate dynamics. He has built a diverse research group with theoretical and observational capabilities. Observation tools include HF radar, ocean mooring, surface drifter, and ocean gliders. And in recent years, he has been involved in the theory development and application of Lagrangian dynamics, including the introduction of a new family of Lagrangian diagnostics for ocean mixing, which is easy to compute, provide new insights regarding the mixing properties on both short and long time scales. So I switch off my sound and the floor is yours.
Okay, thank you. I'm sorry for the light. We have an electric cut now due to the weather. So I hope my battery will survive till the rest of the presentation. So what I'm going to present is a joint work, and actually most of the work was done by Dan Ace, who couldn't attend this meeting, so I'll present it instead of him. And I will show you the result of assimilating glider data into an operational ocean model around Cyprus. And you can find more details in a joint paper in a Deep Sea Research by 2019. Okay, and I guess you're all familiar that the Eastern Mediterranean is a zoo of mesoscale and sub-mesoscale eddies. What you can see here are the results of a numerical simulation by a model by Croco, which was run in a nested grid by a group in Tel Aviv University, and this is taken from Solodov et al. DC last year. Actually, and we can see different snapshots of the vorticity normalized by the Coriolis force, and we can see some differences on the left from the summer season, and on the right when we start the vertical mixing, and the features are a little bit smaller in size. But anyway, it's pretty amazing, you know, how many filaments and eddies and on all kind of scales we have in this domain. And you can also see some observations of eddy using surface drifters. So here you can see a few drifters that were trapped within the Cyprus eddies. This is from a paper again from last year by Polen. And in the right figure, what you can see now are some results of again of a few drifters. And what you can see from this is how variable are the eddies in these areas. So all the drifters that you can see were released on the same date, but you can see, for example, that the yellow one passes through this area in March and just continue, wasn't attracted. Then another one passed through this area in April. Then a drifter that arrived in early August was trapped here in this eddy for a few months, and then another one that was ejected from the Cyprus eddies and again enter into this area, again stay here for a very short while. So all these eddies are very dynamic. They can move from one place to another. And maybe the last example is this one. You can see here two drifters that were released a few minutes from each other, less than 1 kilometer apart. And you can see that after about 10 days, one of them arrived to Cyprus and the other one to Alexandria. So this is a really nice demonstration of the chaotic mixing that we have in the Mediterranean Sea and how sensitive it is to the location of the deployment. So there are many, Dan did many glider sections through the Cyprus eddies. What you can see here is one example from January 2012. You can see in the upper panel the salinity and in the lower panel the temperature. And the most important part in the message from this figure is that during this period, it was mainly a subsurface eddy. So there was very little surface signature of the existence of the eddy. I will not show it, but if you look on satellite data, again, you can hardly notice the existence of the Cyprus eddy during this period. And this is the time that we choose in order to assimilate the data into the model. So the model is the Cyprus operational model. It's called the SciCom. So it's a model that is nested into Alermo, which by itself is nested into MFS. So you can see here the domain of the SciCom model. The horizontal resolution is about 1 kilometer. There's, I think, maybe 24 vertical layers, and it is forced by Skylon, by the Greek model. What we did is like every day, and we did it for a few months, every day you run a hindcast model for 2.5 days to the past. So T0 is the present day. You compare the model result to the observations, in this case to the observations by the glider. And then using OceanVar, you correct the initial condition, then you run it again for another day and a half. Again, compare the model result to the glider, do another correction, and then you restart the model and run it in a forecast mode for 0.45 days. And every day you repeat this process at noon, and we did it for about 6 months. So here you can see 2 examples from day 49 and day 174. They started from December 2011, and we see here 2012. And you can see here salinity differences, or salinity, differences between and where we corrected the salinity using the glider data in the top 2 panels. And in the lower panels, you can see the differences between the simulation in which we did the simulated glider and the simulation in which we didn't. So I didn't mention it in the previous slides. We did one control experiment, which is basically the same, just without the simulation of the glider data. Again, taking all the initial condition, boundary condition from Alermo, and all this nesting worked the same, but in one of them we assimilated the temperature and salinity from the glider, and in the control experiment we didn't. So you can see here in the lower panel the differences in the salinity at a depth of 360 meters between the simulation with the simulation and the simulation without the simulation. And here you can see differences in the surface SST and the surface currents. Again, in the lower panel, this is the data simulation one, and in the upper panel, this is the control one. So clearly, you can see some signature of the surface circulation, the eddy, in the simulation one, and you can also see significant variations in the sea surface temperature. What you can see here is, so we took the 2 velocity fields produced by the 2 model, by the control experiment, and the control experiment actually assimilate other data sources, sea level height and Argo floats and so on, but not the glider data. So we deployed the kind of a few thousand particles in the blue rectangle. what you can see is the red dots are the final location after about 7 or 8 days. The black are the tail of the last 6 days, and in the gray area you can see all the places which the particles visited during the simulation. So it is very clear that you can see very large differences in between the right panel, between the data simulation model and between the control model. You can treat these particles, for example, as any kind of pollutant, oil spill, or whatever. And you can see it now in simulations. So again, the right one is the data simulation, the left is the control. So again, you can see that the assimilation of the glider actually produce a very different surface velocity field, very different salinity and temperature distribution, and so on. So if to conclude, being subsurface, at least in this case of the Cyprus eddy, surface drifters could not have provided any details on the existence of this eddy, at least for the specific days of the experiment. There were no ships and no floats that sample this area, so the glider was the only source of information for the existence of this subsurface eddy. And this specific experiment actually illustrates the value of this glider data when you introduce them into a high-resolution operational model. And you can see a very effective improvement of the model skill by using a single glider. And this single glider cross-sects this area for a few months on a single mission. The time scale where the assimilation of the glider improved the forecast ranges from about 1 day to, let's say, a few days of the geostrophic turbulence dissipation timescale. It's difficult to know the spatial scale of improvement because we didn't have too much data to compare the assimilative model result with the control and with observations. We did notice that the effect of the assimilation is very far-reach. So even on the other side of Cyprus or close to Turkey, there were significant differences. You saw part of them in the salinity, in the temperature, in the velocity fields, but we cannot say for sure that the assimilative results are much improved compared with the control, because we didn't compare the model result to any data in other places. But certainly this was a further study to see what is the spatial scale of the improvement. And thank you.
Thank you. That was really interesting. Who has a question or a comment? Laurent, you unmuted. I think that it's general.
No, it was to be ready. I leave the floor for questions.
And always remember, a bad day at sea is better than a good day at the office.
Yeah. Right.
So I have a question. So I don't know if it Ali, proceed. Go ahead.
Okay, Ali, and then Laurent.
Yeah. Thank you very much. Thanks for the presentation, Hedzi and Barak. I'm at CMCC as one of the co-authors of this presentation, like Serjan, and I had the opportunity to work with him in the past, and also one of the maintainers now at CMCC of the data simulation called OceanWire.
Mm-hmm.
So happy to follow this presentation. Now I'm responsible of the Mediterranean Marine Forecasting Center for the Copernicus Marine Service, and we are starting to assimilate the glider observations also in the Mediterranean Sea. Mm-hmm. And recently we had a study in the EuroSea project, which is a European project, in which we did some experiments to assimilate the glider observations, but they are mostly accumulated in the Western basin. So I was wondering if there's a chance to access the data of gliders in the eastern part of the Mediterranean Sea. Can you guide me a little bit on that? If we have, even in the past, do you release the data of glider measurements in some platform or in some online service?
So we didn't deposit them anywhere, but I don't think it should be a problem to share with you the data of previous missions. Unfortunately, yet maybe Barak can correct me, because we all the time try to persuade the Ministry of Environmental Protection to fund some constant lines that constant transects that we will be able to do with the glider, at least in a kind of a monitoring mode. But so far we don't use them on an operational basis, but I can certainly provide you data from previous missions. Just, let me in touch by email after that.
Yeah, thank you. I mean, not only for the near real time, but also for the reanalysis purposes, for example, it would be very helpful for us. Yeah. Thank you very much.
Thank you. Laurent?
Yes, to answer your question, Ali, I think all data from Dan Hayes, I don't know if Dan is connected. I'm quite sure that they are available at Coriolis. So, and I can, you certainly, I can give you the way to get them, but they are easily fundable. But concerning the Sea Explorer, there is now an operational data flow which is available for everybody who deposit its data to Coriolis. So if somebody having a Sea Explorer wants to have its data quality control in real time, etc., that's available. So you should, Rezi or Barak, you can just FTP your data when the glider surface, and that's it. In some way, your data are treated at once. So okay. And I have a question for you, Rezi.
Yes.
It's so even if we didn't did it in that exercise, so I think it was published, but there was a paper by Barboni et al. Showing the attractive potential of the Cypressidae for in particular merging other eddies. So you can see the Cypressidae as a kind of accumulation area. So numerically, you could test this hypothesis and then see if in terms of pollution, because it's a webinar on pollution, if this could be actually a real accumulation area. In other words, so you have a kind of risk which is homogeneous in the area because of the traffic or of release of oil. So you could imagine a kind of accumulation, either landing or accumulation offshore, where for sure it will be degraded, but it could be an interesting hypothesis to test, to see if some areas are under a kind of permanent pollution risk because they accumulate the surface pollution. Any comment?
Yeah, actually, I don't see it necessarily as a risk, but also as an opportunity. So if, most of the pollution is attracted to a small attractor or a specific location, it actually might make it easier to clean it.
Yes, maybe. But
yeah.
Not yes, it is offshore. Okay.
Yeah, it is offshore. So yeah,
Barak?
interesting. Yeah, we can also actually test it in the model. Try to distribute particles in different places and try to see if there are fewer specific attractors in the basins.
Yes.
Nice idea.
In fact, Barboni did it with Aviso data, so counting from altimetry. And it was a master and then a PhD, but I'm quite sure that it is published, and it was really enlightening. And by the way, the Latakia ID, so you show some tracks of float, showing also a kind of potential of accumulation in the northeast of Cyprus. So of
Yeah, I
Lebanon
will
or
check
of
it.
Syria. So
Mhm. Yeah,
Thank you.
thanks.
Barak, you raise your hand?
Yeah. First, with regard to what Ali was asking, I don't know what is the present situation, but till a year ago, I think, we used the data center of LCMR, El-Semir. So I don't know how, maybe Laurent can tell me how they are connected to if they are connected to the other databases. I don't know.
Maybe Victor has some information on that.
Okay. And with regard to the EDIs, indeed, we actually think, and there are one publication and there are some studies showing that they entrap probably coastal water. And we see higher, in terms of biological parameters, we see higher intensity in the EDIs. So indeed, it seems that they acting as some kind of I don't know if accumulation, but trapping systems for certain elements.
yes, you refer of the so-called Shikmona ID or other that is trapped in coastal waters, or is it,
First of all, also with drifters and buoys, also
Okay.
in the past, we saw that they went, as Hedi showed, but there was some other in the past. We see that they are entrapped, some of them, on eddies. Yeah, there is the Shikmona eddy, which is changing with location, and the Cyprus gyre. But we also, it was published, I think, a year or 2 years ago. We did a comparison of a lot of parameters between anticyclonic and cyclonic eddy and the background situation, and you can see some, I would say, biological parameters that are triggered by nutrients that probably their source is in the coastal water. They are trapped and enhanced inside the eddy.
They're
That's
showing.
what we check.
One last question, comment from Victor, and then I think it will be time to switch off.
Yes, hi, Barak. It was just to explain a little bit more on how Alcemar can help you to publish your data. They have set up a flow that goes directly from Glimpse, the system used to pilot the Sea Glider, to Coriolis with the appropriate data format and metadata information. All goes in through just one button to Coriolis, and Coriolis can run the standard processing chain to feed
Thank you.
European data flow. So you should get in touch with them. I don't know if there's a deal on this service or not, but they have developed this tool and it's very useful. And since it's operational, the number of Sea Glider deployments available on the European DAC is exploding. So it works pretty well.
Okay. And regarding you mentioned HCMR. So HCMR is a Mediterranean entry point for Copernicus in situ TAC. So for delivering non-real-time data, it's the appropriate location. So normally HCMR is supposed to gather the data and then, if I'm not wrong, to distribute them in the data aggregator, CDataNet, EMODNet, yes, CDataNet, EMODNet, yes.
Okay. Well, I think it's maybe the speakers were, if you want to have the last word, you have the right to do it. Else,
For the invitation and for organizing this series.
thank you.
Thank you. Thank you for organizing it.
Thank you.
Yeah, thank you. Very excited.
Okay. So thank you for having joined, and those who want to present something, get in touch with us for the next one. It's always very insightful, and it shows that the gliders can do a lot for the pollution and to monitor it with some monitoring and detecting the oil spills, and also being reactive and putting the gliders as soon as you detect something. So that's very interesting, and it was a very good work. So thank you all, and have a nice evening.
See you next
Thank
time.
you. Bye
Bye-bye.
bye.
Thank you, Martin.
Bye-bye.
Thank you, Barak.
Thank you.
Thank you,
Bye.
bye.